Let us now look at learning theory. So we've spent several weeks looking at different kinds of learners, right? And we actually covered quite a few by now, right? Now you have a good sense of the variety of inductive learning methods that are out there, right? Another thing that you've probably noticed is that there are certain themes that keep recurring, like overfitting, the curse of dimensionality. How much data do I need? Can I be confident that I have learned a good classifier, right? Is this really going to work well on new data, right? And so far we've sort of like done this piecemeal. We said like, well, here's a heuristic way to avoid overfitting in decision trees. Here's a way to avoid overfitting in neural networks. But maybe there are more general ways to deal with these problems, right? Maybe there are good ways to explain when a classifier is doing well and not doing well, right? You've just ran your bag of tricks and nothing is working. Right? This is a common experience, right? Usually what happens in practice is one of three things. Nothing works. Everything works. There's problems on which everything works right out of the bat. They're easy, you're off to the races. Some problems, there's a couple of things that work, but maybe not quite as well as you'd want to. So in those and in the ones where nothing works, now you need to figure out what should I do, right? Are there some general ideas that you can sort of like have in your toolkit, independent of the particular domain or the particular algorithm? Indeed, there are. And that's what we're going to see today. Okay. So the first thing that we're going to look at is a very famous result in machine learning called the no free lunch theorems. Right? You've heard the expression that there's no free lunch, but in machine learning this actually has a very precise technical meaning, and we will see what it is. And it's going to be very shocking, so be prepared. Don't have a heart attack. And then we're going to look at these notions that I already alluded to a couple of times of bias and variance. Bias and variance are, two of the most useful things that a machine learner could have. And then we're going to look at PAC learning. PAC is not political action committee. It's probably approximately correct. Okay. There's also 6-pack learning, which you do once you're starting to get happy. But this PAC, the probably the P stands for probably, and the A stands for approximately, and C for correct. So this is probably approximately correct learning. And this is a bit of a mouthful, but by hedging it twice, probably and approximately, you can get a lot of results, right? Leslie Valiant got the Turing Award for this. Big deal. Right? Back in the 60s, people had all these negative results about the things that you couldn't learn. And it was kind of demoralizing for a while. But once you go into the PAC framework, suddenly a lot of interesting things happen. Okay, so, worthy of a Turing Award. And then we're going to look at the notion of VC dimension. VC is short for Vapnik-Chervonenkis. Vapnik and Chervonenkis are two Russian scientists that invented this notion. And what it's going to allow us to do is to generalize the notions of PAC learning to continuous spaces. So first we're going to look at discrete hypotheses over the discrete attributes like Boolean, but then we're going to want to generalize this to continuous spaces like Rn, and VC dimension lets us do that. Okay, and then next week we're going to look at a major application of these ideas, which is support vector machines. So support vector machines are one of the best performing and most popular types of learning these days, and they basically come out of this theory. Okay? So another reason why it's worth knowing this stuff is that it's going to lay the groundwork for support vector machines next week. Okay? All right.